Our speaker today is Clive Neal. He's currently on a ship in the middle of the ocean, so hopefully we can get the technical difficulties fixed here in a second. But so Clive, he describes himself as a lunar evangelist. He's a professor of planetary geology at the University of Notre Dame. He has over 35 years of experience in studying all aspects of the moon and lunar exploration. He is passionate about establishing human performance on the moon in a way that benefits society here on Earth, while maximizing scientific return that enables commercial involvement. Neal grew up and was educated in the United Kingdom, and he recently became a United States citizen in 2013. He obtained his PhD in geology/geochemistry from the University of Leeds in the United Kingdom in 1986. He then moved to the United States later in that year, where he spent 4 years as a postdoctoral research fellow at the University of Tennessee, Knoxville, studying Apollo samples. He is currently a professor of planetary geology at the University of Notre Dame in Indiana. Clive continues to publish his research and has over 145 peer-reviewed scientific journals. He was a co-editor on New Views of the Moon and New Views of the Moon 2 volumes. He is also the chair of NASA's Lunar Exploration Analysis Group from 2006 through 2010, where he led a community effort to develop the exploration roadmap. And again from 2015 to 2018, where he formed the lead commercial advisory board. In 2015, he received the NASA Wargo Award for contributions to the integration of exploration and planetary science throughout his career. In 2019, Neal was invited to give testimony at the 6th meeting of the National Space Council at the Smithsonian's Udvar-Hazy Center in Chantilly, Virginia, for focusing on the importance of in situ resource utilization. In 2021, Neal received the League Service Award, and of course, he is currently a member of the European Space Agency Human Spaceflight and Exploration Science Advisory Committee, or HESAC, and also steering a committee on the committee member on the NASAM study for non-polar Artemis sites. And I promise that is the end. But Clive, we are so happy to have you.
So thanks everyone for joining today. I'm hoping that this signal will last, because we're sailing in parts which doesn't have much connection. So I'm going to be talking about lunar resources. You've seen the title. But I always put this quote up when I'm talking about the moon, because I think it's rather poignant that back in the early 80s, when this was actually written, it was published posthumously, but Kraft Ericke made that very important statement: if God wanted humans to become a spacefaring species, he would have given them a moon. And lo and behold, we have a moon, and we want to become a spacefaring species. And you can see that, and this is the motivation for the talk, because we look at the Artemis architecture segments. You can see the human lunar return, foundational exploration, sustained lunar evolution, and then we bog off to somewhere that I really don't care about. And what you can see during during foundational exploration, and Artemis 1 through 3 will be the human lunar return, and then the foundational exploration will occur after that. We get demonstration of ISRU, and we will locate resources. If we look at sustained lunar evolution, we will map out resource reserves and start using ISRU, and then demonstrate and utilize ISRU on Mars if and when humans actually get there. As I say, that's going to be when I'm long gone. So as I say, we'll focus on the near term, because we need to learn how to live and work productively off planet close to home before we stampede to Mars. More motivation comes from the Artemis architecture definition document from 2023. And you can see here on page 22, it states to minimize the risk to the Artemis campaign and ISRU product customers, NASA and its partners must plan for a transition from Earth-delivered to ISRU-derived products, along with adequate resource mapping and demonstration of the ISRU process and product quality. Then on page 145, it says the shift from reconnaissance, initial resource assessment and sampling to resource reserve estimation, acquisition and processing occurs during foundational exploration. And reading that document, over 200 pages of a riveting read, the big question comes out is how? How is that going to happen? Because it is never articulated in the architecture, and right now there is nothing planned for mapping resources, because if you propose to the Lunar Data Analysis Program to do a resource mapping, prospectivity mapping exercise, you get turned down and discouraged because they do science, they don't do prospecting. And I hope to convince you that by doing prospecting, you will be doing science by the end of this talk. But the first thing we got to go through is what are the lunar resources. This may be known to some of you, but maybe not others. So I'm just going to shoot through this rather quickly. We talk about polar volatile deposits, and we normally focus on water ice at the poles that has been detected. And why we're putting a base at the South Pole is to take advantage of those in situ resources in order for life support and rocket fuel. But something that I've been thinking about, and I know others have been thinking about, is if that hydrogen that is known to be there is from the solar wind, how much helium is going to be there as well? And I want you to keep that in the back of your mind as we go through this, because that has important implications for a byproduct that could be a potential export. We've also got regolith, and you can see there building materials, metals, oxygen, solar wind implanted volatiles, hydrogen, helium, carbon, nitrogen, etc. Platinum group metals, which predominantly come from impactors, and then the rare earth elements and thorium and uranium in the Procellarum Crete terrain. And then we get pyroclastic deposits, volatiles. We now know from M-Cube data that some of these pyroclastics do have a hydration signature much above those measured in the pyroclastic glasses returned by Apollo 15 and Apollo 17. And because they are glass, it's easier to melt than crystalline substances, and they're a ready source of metals if we can extract them. And then we end up with structures on the lunar surface, the lava tubes and impact craters, which are other potential resources that could be utilized to enable many things that I'll get to as we go through this. Another way to look at this, and there's basically three types. Those the resources that would be of use for in situ use, potential export off moon, or both. And water can be used in situ or could be transported off in terms of rocket fuel. So you can see it's there in the green. And I highlight helium-3, which could potentially also be an important polar volatile deposit, which is going to be an export back to Earth. And we actually have companies already having contracts signed to deliver helium-3 from the moon back here on Earth. So this is becoming a reality, although we still need to demonstrate that helium-3 can be captured and successfully mined on the moon. We look at the regoliths. You can see building materials, metals, oxygen, solar wind implanted volatiles, apart from helium there, are all going to be used in situ. Platinum group metals and rare earth elements could be a potential export, depending upon the prices of these particular elements back on this planet. And then thorium, uranium, if we're putting fission reactors up there, we really need fuel to put more up there and become self-sufficient. And I'm thinking long term here, but we know that there are enrichments in thorium, uranium. Pyroclastic deposits, the volatiles, again, both export and in situ use in the metals for in situ. And of course, the structures, as they're on the moon, are going to be used in situ. So the moon is not as dry as first thought, because after Apollo, it was considered to be very dry, although bones are quite aqueous, but we'll gloss over that bit. But again, since Apollo, we now know that there's buried hydrogen and water at the poles via radar and neutron data, and also the impactor, the L-cross impactor. We've got the diurnal surface water cycle that we've got from M-cubed data from Chandrayaan-1 and SOFIA observations, hydrated pyroclastic deposits, again, M-cubed and sample analysis, and mature regolith contains solar wind hydrogen that when heated up can actually cause a reduction and you get water coming out. So the regolith maturity becomes important both in terms of hydrogen and helium. How much is there? Well, we really don't know what the true value of solar wind and mature regolith is. because we've never measured it in situ. Once regolith has been sampled, it's been jiggled around a fair bit, getting it out of the lunar regolith into a capsule and then back to Earth. And again, we really need to know more from in situ analysis. If we look at the diurnal surface here, we're dealing with nanograms per gram because it's only a surface water layer. For pyroclastic deposits from both sample analysis and also from orbital data, we get 30 to more than 300 part per million. And then we get to the polar volatiles, again, the mother lode, if you like. And you can see Feldman et al. Quoted 3 billion tons of water ice at each pole on the basis of lunar prospector data, very coarse-grained data. But there could also be helium-3 there if there is a lot of solar wind being captured in those cold traps. And our 1 point of ground truth there, Cabeus, 5.6 weight percent, is something to keep in mind as we go through this. But again, are all cold traps at the South and North Pole going to contain 5.6 weight percent water? Are there going to be some that are going to be richer? Others are going to be poorer? We just don't know. If we look at the regolith, and you can see here on the table on the right, you can get a lot of metals and other elements out of that, as well as oxygen. Those metals can be used for construction, human health, and agriculture. And if we then sort of look at oxygen, you can see that oxygen from regolith anywhere on the surface of the moon is going to give you about the same percentage, between about 43, 44 weight percent oxygen coming out of that. And then we have the regolith as a basically raw material or a building material for concrete, lunar concrete, and 3D printing source materials. But if we're going to liberate the metals and oxygen, we need to use molten regolith electrolysis. And the problem with this, it works really well in 1G, but will it work in 16G? And I've listed here a number of papers that seem to indicate there's going to be problems if we try and do this on the surface of the moon, because the viscosity is going to be so great that the buoyancy forces of the bubbles generated at the electrode is not strong enough to get through that and leave, such that you end up adding an infinite resistance to your electrolysis and it just shuts down. So there's work in situ that needs to be done there. If you look at the solar wind, it bathes the lunar surface in volatiles, and I'll highlight the solar wind: carbon, nitrogen, hydrogen, helium. These are the solar wind implanted volatiles, and they can combine with oxygen and hydrogen to give other molecules there, as you see. But this is an important thing: is how long does regolith take to become mature? And I've seen estimations from many thousands of years to millions of years down to 100 years. So which is it? Well, we really don't know. Do we have a renewable resource in terms of we could harvest the solar wind and treat it like a forest here on Earth, where we would then leave it out in the solar wind for more implantation and then come back 100 years later and do it, if that is how long that it takes. So we can see that these elements, they correspond nicely with the maturity index, I sub S over FeO. And you can see that the more mature the regolith, the higher the concentration of these elements. And again, ilmenite is something I refer to as our little sponge on the moon. It holds on to solar winds implanted species much better than other minerals, and you can see that in the data that are down in the just below this text here on the right. Helium-3 is a potential lunar export and is critical for aneutronic fusion and is rare on Earth. Most of the companies that I know of are going to the mature ilmenite-rich regolith, but I wouldn't discount the cold traps at the poles for significant helium-3, but we really don't know anything about it. Helium was not identified by the L-cross impactor, and I'm not sure whether that was because there was none there or that it wasn't able to detect it. So you can see here one sort of schematic of helium deuterium fusion. It gives quite a bit of energy, as does the two helium 3s coming together to give you again a lot of energy. And again, being aneutronic, there are no toxic byproducts from this process. That's the nirvana of the fusion process. And so, but again, only we've had a small sustainable fusion reaction in this country, but it's South Korea and China that are leading the way with multi-minute sustainable fusion reactions, and that technology is coming on in leaps and bounds. And the other question that I'm posing here is the moon the answer to the critical mineral or metal shortage? And I highlight here rare earths and uranium thorium again, and you can see that just with the coarse-grained Lunar Prospector mission, we can see significant enrichments. They were detecting samarium with their gamma ray spectrometer, and you can see significant enrichments in Imbrium ejecta. And it's interesting that the thorium anomaly is also correlated with the Imbrium ejecta as it goes around that particular crater. So it's how much is there? Well, we really don't know. This is a very coarse look. We know that in the resolution of the prospector data, there is an enrichment, but that's about 40 kilometers squared per pixel. So is that 1 kilometer within there that does it? We don't know, and it requires further analysis. And then we talk about the platinum group elements here, and these all come from extra lunar sources, the chondrites and the iron meteorites and asteroids. And you can see here in this platinum osmium plot from James Day and co-authors reviews in Mineralogy Geochemistry paper from 2016, that we have quite an enrichment in the ions up the top here. Chondrites a little lower, and then the moon is well depleted in those particular elements. And so we're looking for concentrations, particularly of ions, that would give us potentially enrichments high enough, depending upon the price, to make it economic to go harvest and bring back to Earth. So pyroclastic deposits could represent more accessible metal and volatile resources. And the reason I state that is if you look at the compositions, they have a higher iron silicon ratio. And we know that from the samples that were brought back 36 years after they were collected, it was shown that they did contain water. We've seen that from orbit. And if we again look at the orbital data, I highlight Aristarchus here, again from Ralph Millikan and Shuai Li's paper back in 2017. Glasses are going to be easier to melt than regolith. They contain quite a bit of water compared to the surrounding area, and this lower viscosity may be enough to enable molten regolith electrolysis to allow metal purification and separation from that particular regolith sample. And then finally, landforms. These are another potential resource here, and you see lava tubes, and everybody talks about lava tubes as potential human habitats. But on the moon, most of the images we have are shown below there from Mare Ingenae of these skylights that are there, that have been reported. The interesting thing about this is what do you need for protection for humans? Well, you need to protect them from radiation, meteoroids, and thermal swings. And putting a habitat in a lava tube is going to do that without having to engineer something. Or if you go to the South Pole, how are you going to do that? Well, you're going to have to bury it. I think the modeling that I've seen is about 2 to 5 meters of regolith in order to protect for those thermal swings, and also from, more importantly, from the radiation and micrometeoroids. And again, you can see the work that's been done. The average temperature is about -20°C all year. And that was done by Fred Hertz back in 1986. Just because it's old doesn't mean to say it's wrong. And Impact craters, launch and landing pads construction, because it's a depression. They have natural berms around them. And if they're a simple crater, there would be hopefully enough area there to actually have a ready-made launch and landing pad. And there could also be locations for large telescopes on the far side, again, off in the future, but something near at hand is these launch and landing pads. One of the most critical things that we need is a launch landing pad for Artemis 3. As in my opinion, I don't think Starship is going to be able to bring the humans back. I mean, if it can land and not fall over, that would be a massive improvement, and it would certainly exceed my expectations. But if when it takes off, and we've seen what happens with Starship in the first test, it blew up its own purpose-built launch and landing pad, knocked out 7 Raptor engines, and we lost the mission. Now you're going to take off with humans on board from loose regolith. What could possibly go wrong with that? So something that we could use the local geology to actually tell us or develop this launch landing pad. So something that I've been espousing is that the United Nations is ready to regulate in situ resource utilization. But the trouble is, lunar resources are not ready for extraction or use because their reserve potential is unknown. And again, finding resources is not sufficient to start this extraction. And then we need to understand the existence of reserves or reserve potential. And I give you this definition from the USGS between of resource and reserve. And I've highlighted the important thing here, economics, because if we have reserves, this is something that is going to be of interest to the commercial sector. And if we're going to have a vibrant cislunar economy that comes out of this human space exploration, we need the commercials involved. Until we can prove the reserve potential of these resources, they will not be involved. So this is something that becomes front and center, and this is something that I've been trying to champion for the last several years now, that we need a resource prospecting campaign. Yeah, and that's the reason being is defining reserves is an iterative exercise, and you can see that from Cannon and Britt's work back in 2020. And as of today, there are no recognized reserves at the moon. And you may say, well, oxygen from regolith. Okay. The reserves require economics. Where's the market? Okay, you can get it anywhere. It is not a reserve until you can make a profit from it. So it might be everywhere, and we don't even know if we can extract it, because molten regolith electrolysis may not even work with or without a salt on the surface of the moon. So to answer the question, are lunar resources enabling assets or futuristic unobtanium, we're going to need more data. And that's why we need those data to actually look at the reserve potential. They need to be more granular. And the only way we're going to get these more granular data sets is through prospecting campaigns. And you can see in the table here, the types of data that we need: composition, form, distribution, geotechnical, which is often overlooked. Can you actually extract it from the regolith? If you're dealing with water ice, is it cementing the regolith? And if you're at 40 Kelvin, that cement is going to be really, really difficult to get out. So we need to understand the near surface regolith stratigraphy. How close to the surface is it? Can we actually reach it again? And accessibility, can we actually get to the deposits on the surface to actually extract it? So there's lots of things we don't know. We know that there are resources. We have no clue about reserve potential, but what we do know are the data that are needed in order to show that. The other thing is to look at what has been done already in the literature. And Holly Brown's paper in 2022 ranked using LRO and prospector data the 10 most promising sites for polar volatiles, using the large permanently shadowed regions at the poles. And the top 10 cover over 5,900 square kilometers. And that's quite a lot of land to cover with mobile assets. So we need to do better with our orbital data. But again, I highlight, no resource prospecting campaign has been conducted on the moon, and none, listen to me, none are being planned. But prospecting campaigns will deliver data that inform multiple stakeholders. And I put up this little Venn diagram here about lunar volatile resources. What data would we need? And again, you can see here that there's a lot of overlap between science exploration and commerce. You get a lot of science out of prospecting. And this is something that is important to mention to NASA. The other thing that's been really annoying me is the fact that at the United Nations, there are people that want to protect areas that contain resources because they want to protect it for the science. Prospecting will deliver the science data on these areas. Is there a question? Got a live mic there. Prospecting will deliver science data on these areas' environments that otherwise would likely not be visited. And this is the thing, you can protect these areas and not allow commercial entities or anything else go in there. But then science missions, which are usually competitive PI missions, will likely never visit them. So if you look at the Outer Space Treaty, Article 1, Paragraph 2, protection of areas that contain resources for science is actually in contravention of that Outer Space Treaty. Interesting to see that. So when we go to the moon, Mars and beyond, we should go together. And that means science, exploration and commerce go together because the data inform multiple stakeholders and you get an awful lot of science done if you're doing prospecting in a scientifically sensitive, if you like, region. But if we go together, everybody's informed of what those sensitivities are. Campaigns require cooperation then between science, exploration, commerce, and international agencies for the very reason I pointed out earlier about the actual area that you have to explore in order to find these resources. But prospecting campaigns to characterize resources in their environments are the immediate next step for the moon because they're going to form partnerships between different communities. And there's also amazing opportunities for international cooperation, development of interoperability standards and promotion of information sharing protocols. And resource utilization is going to be in the future, but we have to have science involved. If we're going to start mining a resource, scientists have to be embedded in that operation and follow the construction model in Europe. And for those of you that are not familiar with that, if there is construction and excavations going on in Europe and they come across an archaeological site, everything stops and the science gets done. And that science would not have gotten done if there was never any construction. It would just be left covered up. And this is something I think that could be followed for resource utilization and mining on the moon. And because science and exploration enable each other, and both will enable commerce. So a group of us got together, and you can see here from this 2024 paper in Acta Astronautica, we've started to create this international lunar resource prospecting campaign, and this has begun for polar volatiles. And basically what we're trying to do is to coordinate existing and future missions. And you can see the list there that have agreed to be part of this. You can see the orbital ones. You can see the LRO, of course. You can see the KPLO from Korea and Chandrayaan-2. And then you've got the landed ones. You've got Viper, maybe Artemis 3. I don't think it will do much good in telling us about volatiles at the South Pole. We got Lupex, and then we got the ESA Prospect lander going on Eclipse mission. So there are now 26 scheduled missions to the moon before 2030. These may be of use to tell us about volatiles, but nobody is coordinating them. So it's something that we've been pushing and been contacting those in charge of those missions to try and get their cooperation in this. And what we've asked them to focus on are not these large, big PSRs, which would be difficult to get into. I mean, if you look at Shackleton Crater highlighted there on the map, it is potentially a very good target, but you land in the quasi-permanent sunlight of the rim, but then you have to go down 4.5 kilometers of a 30 to 35 degree slope into something that's about 40 Kelvin in order to actually access the resource that's there. So it may not be accessible. So focusing on these smaller ones highlighted in light blue there and in different groupings, we are starting to look at mapping out traversability paths into these, to look at the distribution based upon the very coarse-grained orbital data of the volatiles on the surface and the subsurface. And this should be a good proof of concept. And again, by integrating the different data sets to generate prospectivity maps, we may actually be able to start putting some quantitation into the reserve potential of these polar volatiles. So, in summary, you've got the list here, again, going back to the beginning of the potential lunar resources for in situ use for export or both. And you can see them again highlighted there in this particular slide. And then to answer the question, are lunar resources enabling assets or futuristic unobtanium? We do need more data. I can't answer that question right now. The only prospecting mission we had, NASA is trying to cancel. So I think we should fly Viper, and I'm hoping Viper will be at the moon within the next year or so. And we will be able to start answering some of these questions along with the international partners that you saw on the slide a couple of slides ago. They're agreeing to be part of this international lunar resource prospecting campaign. So the take-home messages from this presentation are as follows. The moon contains many potential resources for use in situ, for export, or both. We've also got something we have to do. We have to prove the resources are reserves, and that's going to be critical for commercial involvement and creating a permanent human presence on the moon, which is articulated explicitly in our current space policy, which was from President Trump's first term. It was not changed during Biden's term as president, and it is still the space policy of this country. This is the first time a space policy has transcended an administration change since Apollo. So there is a lot of hope that we have a robust space policy that is generating jobs because of the commercial sector. Resource prospecting is going to inform science exploration, commercial activities, and it promotes international cooperation and collaboration, as well as interoperability and information sharing protocols. And then coordination of ongoing and scheduled lunar missions can be powerful in advancing resource prospecting, because campaigns equals lots of missions, which equals lots of money. And the reason why we can start to coordinate these missions that are already going, we will get the ground truth data that are critical for understanding if we have an enabling asset or futuristic unobtanium in these resources on the moon. And this International Lunar Resource Prospecting campaign has started this process. And again, are lunar resources enabling assets or futuristic unobtanium? More data are needed. Thank you very much.
Wonderful, Clive. Thank you so much. And then, yeah, we'll go ahead and open this up for questions. So if you have a question and you're online, go ahead, raise your hand, or if you want, you can put it in the chat. And then for us here in person, if anybody has a question, just throw something or shout it. Go ahead, Chip.
Great, thank you so much for doing this for us. This was great.
It's going to cost you. So.
Yeah. The question I had for you, well, I had lots of questions, but the first one is, Antarctica has a special treaty that prohibits or limits exploration, prospecting, and development of resources in Antarctica. How is the moon different right now in terms of what people are considering the moon, and how does it differ from Antarctica?
Okay, right now, the only thing governing the moon in terms of resources is the Outer Space Treaty. And it doesn't really concern resources. It doesn't really mention them. It says you can't own land on the moon. And this is something now. There is now a working group on the legal aspects of space resource utilization that is trying to set up a framework for governance of space resource utilization. And this is something I went to Vienna to as part of the US delegation in May to talk to them about this. And part of this presentation, I used some slides saying that we're nowhere near ready to use resources on the moon. I think you need to have data in order to properly create this governance structure. For example, if we find out that there are 3 PSRs on the moon that have reserve potential, the governance structure for actually going in and using those is going to be very different than if we had 3,000. And this is the type of thing that needs to be done, because everybody's stampeding to sort of regulate it and put legal structures in place on the basis of no data. And I think we've done ourselves a disservice in that we keep using the term resource when we mean reserve. And that leads everybody to think that, well, we know where they are, we just need to go get them. And whoever gets there first is going to get them all. And that is just not true. So right now, Outer Space Treaty is it. I have become quite familiar with the Outer Space Treaty. And it is not a long read, but it is quite informative. And that's what I picked up on when I was at the UN about these protection of sites of scientific value. And again, I'm totally against it, because we would never get to visit them, especially given the current climate in the US. Maybe other nations will, but I don't see that. So it's time that we go together. And if we can go together, we will get an awful lot of science done. If we go together with exploration and commerce to look at some of these sites. But again, we all go together, or we don't go at all.
Well, thank you, Chip. Thank you, Clive. Any other questions? Well, go ahead, Chip.
Is there anybody else on that going to ask a question?
I'm not seeing any hands up, and I'm not seeing anything in the chat. So,
Okay.
Chip, if you want to go again, you're fine.
Yeah, Clive, just out of curiosity, is there any sort of, for prospecting, one may need a variety of different tools than one would need for just science exploration of the geology of the moon? Like, for example, one would want to assay, if you will, to some degree, the volatile deposits and coal traps. What sort of technology development has there been to collect those samples in the state that they're in and return them to Earth, where they can be assayed and we have a better understanding of what that really deposit is? Clearly, if you're looking for gold on Earth, you do fire assays and assays for gold. But what sort of technologies are there available or being developed to do that on the moon for volatiles?
Yeah, you're talking about cryogenic sample return, and I've become very finicky about definitions. So what do people mean by cryogenic? Normally it means minus 80 Celsius. For cold trap samples, that is woefully inadequate. And the samples put in minus 80 would be heated up substantially. So I think that we need to change and develop assaying techniques that can be done in situ. And that's a technology development that's needed. And it's why I like the Viper idea of actually analyzing the material that's come up in the auger drill as it gets to the surface, and you can then find out what the issue is with the what the concentration is, and you can then equate that with depth of the drill. And that is one way to do that. If you want to do an isotopic analysis, they had a mass spectrometer on there that would be able to give you a very, very broad brush isotopic analysis, which would tell you whether or not you've got solar wind hydrogen versus cometary hydrogen. So there are things that have been developed that can be used. There's work to be done. But the idea of bringing back, especially if you're dealing with the polar volatiles in the cold traps, I don't think it's worth the technology development to bring them back. It's the technology development would be needed to actually analyze the samples in situ. And I'm a great fan of sample return, but in terms of scientific, I think we would be able to get 1 or 2 samples back. But when you're assaying, you need a lot of samples, and the mass of a cryogenic sample return container, even at minus 80, is going to be prohibitive to bring back, more than 3 or 4 samples, let alone 100. So we have to think things a little different, I think.
Actually, Clive, I'll follow up with a question on that. So, we've been talking about reserves as making an economic profit, right? Like going there, and these are things that you can make profit off of. So, like we look at our current structure with, even from just clips with Artemis, these are multi-billion-dollar programs. Like Artemis is multi-billion-dollar. So if we go to the moon, are we saying that when we bring back these rare earth elements, or we, can mine this helium-3, that we are going to make profit? That's going to surplus $1 billion. Because that's like the money that we're putting in with Artemis, and like even like Eclipse mission is, still $100 million.
Well, again, you've got commercial companies that have mining helium-3 that have contracts to bring helium-3 back, and they think they can do it and make a profit. This is the new moon order, if you like, is that these commercial companies have been spawned because they think there's a market, and they think they can make a profit on it. So that is something that we need to get out of the mindset of, okay, NASA's going to do everything, because NASA can't. We need to embrace, I think, the commercial sector to, not only allow us to explore the moon, but create jobs for people who are graduating from university, say, that probably we're going to need one. That NASA won't be able to take all of you, but there are now more and more companies out there that are hiring, and that is great to see. And so I think that we've put money investment into NASA because NASA de-risks it. Viper was a de-risker, the pathfinder for de-risking, but it's not there yet. And it's not been cancelled. It was, but then it was, oh no, hold on a minute. No, we're not going to do that now. And then hopefully it will be going to the moon soon and getting the sort of ground truth data we need. So this is the neat thing about ground truth data. Once you get ground truth data, you can then modify your predictive models, and it makes all those orbital data you used in those predictive models much more valuable. You can then make better predictions. You go to another site, you get more ground truth data, you then refine your predictive models. And it's, as I say, it's an iterative approach. You don't throw out the initial data, they actually get better with ground truth. And that is something that I think the commercials are looking at in terms of helium-3. They're going to go prospecting. This is what we think we know. Now you go to the lunar surface, and you actually find out what the true composition of solar wind and mature regolith actually is. We got a minimum with Apollo.
Yeah.
Bits that didn't get knocked off.
Yeah, that's perfect. And it's like, as you had also mentioned in the slides as well, it's not, you had said it's not a NASA thing, like this is multiple nations working together. I'm also curious, like, do you know, is like Department of Energy also like a part of this? Have you guys like talked with Department of Energy potentially for stuff?
We haven't talked to the Department of Energy. The prospecting campaign hasn't, but commercial companies interested in helium-3 have.
Okay.
So and one of the contracts I think has been signed is from the DOE.
Okay. Awesome. Well, thank you, Clive. Any other questions? Whether you're online, again, raise your hand, put something in the chat. Here in person, just throw chalk at me. Go ahead, Chip.
Yeah, I'm sorry, Clive.
Oh, could somebody shut him up, please? Come on.
Well, it's nice talking to you, mate. Both you and I, among many others, really championed the Viper mission, and we're really disappointed that it was canceled. What is the future prospect and hopes and dreams for having a Viper-style mission within the next year or 2 or 3? Because again, it's a valuable first step in this prospecting campaign.
Yep. All I can say is very good.
Yeah. Okay,
That's
good.
all I can say right now. It is. I am very cautiously optimistic. Or is that cautiously very optimistic? How about that?
Well, thank you, Chip. We'll do maybe one more if anyone has any questions for Clive. Well, if not, then Clive, once again, thank you so much for joining us from the high seas. Oh wait, I think we have a new message.
Thanks, Clive.
Yeah, thank you so much, Clive. Thank you for joining us.
All right. No worries. Glad to do it. All right. Talk to you soon, Chip.
All right.
Bye-bye.
And then for everyone else, thank you for joining us. We'll have a Planetary Sample Science Seminar series again next Wednesday, same bat time, same bat place. It'll be Nick Dygert from the University of Tennessee. So hope to see you guys again next week. For now, everyone enjoy the rest of their weeks, your weekends, and have a good time. Thank you.
Bye.